Good evening, everyone. Thank you for coming. Welcome to AES at SAE. It still confuses me. Tonight, I don't actually have many announcements to make before the meeting. Just a couple of thank yous, really. Thank you to SAE yet again for providing this venue for us, this marvellous venue where I hope I can find a seat in a minute. And also thank you to PMC for the provision of these enormous loudspeakers behind me that will soon be playing some wonderful drums and things. And thank you, thirdly, to Giancarlo del Sordo from Acustica. Is it Acustica Audio? You're going to be demonstrating and talking about nonlinear convolution and Nebula. So, as you've already signed in, and I don't have to talk about that, I'll save the other notices till the end of this meeting, and I'll just let you get on with it. Thank you very much, Giancarlo.
Thank you. Do you hear me? Maybe. Okay. Hi, I am Giancarlo del Sordo, and I work for a little company, Italian company, which is specialized in convolution and audio plugins, audio software. Antonello will not be here this evening because he had serious issues. Anyway, he's fine. I tried to substitute and to... Okay. Before starting, it's very important my first slide, because I am an Italian speaker. Maybe my English is not very good, so if you don't understand something, just stop me. I can start again or explain using different words. Okay. But maybe you are a bit lucky, because when I explain my software in Italian, I speak very quickly. so English is forcing me to go slowly and to keep this presentation simple. This presentation there are three main sections. The first one is about our software, so I want just to explain what we are doing, so you have a better picture, for example, on what we are creating, what are our products, and maybe you understand a bit more the second section, which is the lecture itself, which is speaking about the main subject. At the end, there is also a little section, which is a sort of geeky corner, a corner for geeks, which it will be very quick, but you will know about things which were never explained in a public forum or even in other convention papers. There is also a little scoop at the end. Okay. Okay, let's start from the creation of plugins. There is what I call a standard method for creating plugins or audio software or DSP, which is based on analysis. For example, for example, you have a vintage gear, you want to replicate, you want to emulate it in some way. Sometimes you try to get a sort of math formula, or you get electric schema, you use Spice or other software. You get a sort of formula of what is doing this particular DSP unit, and you try to simplify it in some way. The standard approach, in my opinion, is a bit complex, because you need to, sometimes you just copy from convention paper. For example, there is a new research, so you take a new math formula and you just try to create a new plugin. But what makes it very difficult to work with is you need a lot of time in order to validate what you are doing. For example, you have a complex math formula. You are simplify your terms. You are trying to get something which is working on CPU, which is sounding in a right way. But at the end of the day, you need a lot of beta testers, a lot of audio jigs, because they should try to use your invention and try to understand if your plugin, your DSP is working in the correct way. So is also a bit expensive, because you need a lot of time in order to validate it. We have a different approach, which is based on sampling. We are not the only company in the world which is creating DSP using sampling or using convolution. There are other products around. For example, there are SynthFX products, Liquid Channel, Liquid Mix, and also convolution software. For example, Altiverb. So the sampling approach is very common. Sometimes the sampling approach is hidden in some way. For example, there is a company which is, for example, creating a new DSP, sampling, for example, a cabinet. After they try to add guitar models, analog modeling models over it. So there is a sort of hybrid approach to it. But our approach is different for an important feature, in my opinion, because we have a simple software for sampling, which is very easy to use. It's very simple, it's very clean, interface is basic. The whole process is pretty cheap, in my opinion, because when you start sampling and you have, for example, tested this software for a preamp, you can sample other preamps and maybe the result is in the same ballpark. So there is also a sort of validation, for example, from the audio community, because maybe a particular category of preamps are really similar among them. So if you find a good way for modeling tubes, maybe all tubes are modeled in a correct way, or the audio community accept them as good products. Here, a little example of how simple our process is. Here there is a stone box. You just connect your laptop, your computer. There is a simple form, as you can see. You just type the name of what you are sampling. Few details, for example, the name of the file, description. There is gain, period. So simple parameters, and that's all. You just push your sample button, and the software is pretty automatic in this case. What we are sampling exactly? We are not sampling audio source, but there are a lot of passive units. For example, preamps, equalizer, tape devices, amplifiers, reverbs, compressors. So you can see there is a wide range of things we can sample, just using the same approach. And this lecture is about how we are making this possible, just using a sort of unique approach, which seems like a bit magic, because it works and it doesn't depend if your device is much complex, is old, is, for example, there is a sort of cyclic behavior inside or other things. Or, for example, is a compressor, so is a compression audio or is a flanger. Okay, and here I show the software quickly in order to complete. The sampling is a really easy. It's really simple. For example, you have a device which is based on 3 knobs or 3 sliders. You load a session based on 3 knobs, like in this case. You just change name. For example, you are sampling first knob, which is a frequency, second knob, which is a gain. So it's very basic, it's very simple. For each knob or slider, you add all values you are going to sample. For example, you are going to sample 5 steps, 10 steps. So a complex session where you are going to get 100 of values for each knobs. And at the end, the software makes a sort of big sampling session, stopping each time you need to turn, for example, knobs on the real unit, because it can guess what is missing. So, for example, if the gain is behaving in a particular way, you need to move it while, for example, frequency is in a position or in another position, which is very important because there is no way for guessing how will be the final behavior. So as you can see, it's very basic, it's very simple. And just to complete this first quick description, here we have our sampling results. Okay. There is a website from a third-party developer, which is a GUI, who create a sort of list online of what was sampled. And it's pretty long. We speak about it later. And the software is still pretty easy to use. You see during this little demo. So there is an interface. You see, we have different appearance for this interface. For example, sometimes they are minimal. We have knobs, we have sliders. Okay, but in general, it is a general engine where you select a preset and just it changes, and it can be a reverb, it can be an equalizer, it can be a compressor. Okay. For example, now I'm changing the preset. This is the Dolby, for example. I can have, for example, tapes. Just this is a particular tape. Okay. Sometimes they are very clean. Sometimes they are very dirty. Sometimes we have, for example, a filter, or sometimes even, for example, a complex equalizer with more knobs. In this case, a couple of knobs, which is gain, frequency, and so on. Okay. So this was just a first description of what we are doing. So during the lecture, when you see pictures from this plugin, or you see I use it, you know what the product is, what a sample is, what we are doing. Okay. And now let's start from the beginning. This lecture is about the impulse response, which is our main building block. We have a system, we want to model it. This system is linear, is non-varying in time, which is static, we can say. And there is this little impulse response which is modeling it, and is a basic approach. For example, for reverbs, there are companies which are developing plugins based on their technology on, for example, reverb impulse response cabinets, for example, or halls or churches, for example, sounds and so on. Which are the main features? This is the result is clean because your system is linear and is static. So its approach is really basic. You can do a lot of things, for example, filters, static filters, even equalizer. There are a lot of products which are based on it. Anyway, you are pretty limited in some way. This slide is about dynamic convolution. We are not doing dynamic convolution, so I'm explain immediately why we are different. It's very basic as a slide, but I think it is quite effective. What is really dynamic convolution? You have an input assessment, you are measuring your input, and based on the input level, you are selecting a different impulse response, which is really a simple approach, a powerful idea. Like all simple ideas, you can do a lot of things using it. For example, you can model a tape. There is a company which create for the first time emulation basing everything on dynamic convolution, and it is pretty famous. Is Synthefx. But how can we describe this result? The main feature, it is distorted. I'm not using the term distortion because, in my opinion, sometimes this quick switching of the response is creating, for example, aliasing. But this is just a little minus because the technique itself is very powerful, in my opinion. But the main drawback is that there are patents on it. So when we start, we decide to avoid it. Even if we were not going to release hardware products, so patents are main for hardware products, not for software, we decided to take a different approach. And this was our first building block, which is a different approach to convolution. As you can see, the picture is similar to the previous one, but there is a timer inside. We are not doing this selection of the response for each incoming sample, but we are working in blocks. We are trying to get in a sort of context switching, but not for each incoming sample. We are trying to minimize distortion. We are trying to avoid distortion at all. First time we tested this approach, I was really satisfied because, in my opinion, the audio was really alive, like the original one, but distortion was completely not present in this first result. My first feeling was, okay, we have something new, very, very new. We can work on it, and maybe we can build something which is not present on the market. Main feature is clean, like for the static convolution. But is the most important feature, sound is alive. Now I show you in a little demo what I mean. The same audio as before. No, different. This is drum. Okay. And this is the result of our approach. I try to make it really this is a console. As you can see, the original audio is static. There is a little change in game, but mind it. What is important is, like you hear, is more dynamic. There is a sort of is breathing. is moving. You hear more alive. In this case, I use free console emulation in chain in order to make it very obvious. But this approach is very useful when you have, for example, a complex mix. You have a lot of tracks. So you apply an instance of this console emulation on each one, and at the end you have the sum of everything, and it makes the whole mix more obvious. It seems more processed, but at the same time it doesn't change too much. It's just more alive. As you can guess, this is just our first building block. It's not enough. We are just starting. Second question was how to add a control. It's very easy. Here, a simple slide. We have, for example, a pass filter. There is a knob. You can use it for selecting the right response, which is a real basic approach. We are not alone in doing that, so I'm just showing the basic technique. But what we are doing is a clever interpolation. So, for example, when you rotate the knob and you pick an intermediate value, our interpolation is pretty good and is working very well. So you get a sort of intermediate frequency. Again, when you turn your knob, you get a static impulse response. So result is, like before, clean and static. I try to show this. This is the original sample. And here we have gain, frequency. Again, here we have a filter. I removed all distortion because we can do a lot more, but in our first example we are trying to explain which is the basic technique. So you have many controls, many knobs. You have a sort of combination of them. And at the end, when a value is missing, there is a sort of intermediate value which is calculated in some way, because there is a sort of interpolation. It's a bit like audio samplers. Well, you have, for example, you are sampling a violin, a string. For example, you are sampling A, D, F is missing, but it could be guessed, for example, from pitch shifting of one of previous sample. Okay. So this is the basic approach. You can guess. We can go on with a dynamic version, which is a dynamic equalizer. So we take the Acustica convolution, we use it in this EQ model. We have the simple knob as before, but you are not just selecting a single sample. You are selecting a sort of dynamic one, of moving one. Result is a lot better because it's clean but is alive like before. So we are adding controls, we are adding things to our basic model. Okay. For example, this is the original audio. And we have result. As you can see, is moving, is alive. There is also a skin on our product, so it seems more like a real Pultec. Anyway, what seems important is not just the skin, is that you have a lot of controls in this example, and you can switch, you can move them, and the sound is pretty close to the original. It's not perfect yet, because I tuned it in order to simplify and to make just a sort of a dynamic equalizer. It's a lot more the original unit, but in this case you have an idea of the approach. Okay, let's go on. How can we sample a compressor? We are increasing, we are improving our first model, we are adding things. So our basic model is becoming more and more complex. Okay, compressor. You have an envelope follower, an envelope detector, which was present also before in first slides, but it was hidden. It was not in. I omitted in order to not create too much confusion. Okay, so there is an assessment of the input. There is a detector, an assessment of the input, and you are selecting a different group of audio samples, which are, for example, different compression ratio, 4:1, 8:1, and so on. In this basic approach, because it is still basic, the envelope follower is still an algorithmic version of the envelope follower. So there is a code, in this case, simple code, which is just modeling a perfect unit. You know, compressors are never perfect unit. And we are just guessing that our 30 milliseconds are the same of the original unit, which is not true. Anyway, as a basic first approach, this is pretty enough. We have compressor, which is an amazing result. Okay. Here we have a sample, which is a piano. As you can see, there are louder section and quiet sections. And here the same one with a bit of compression. Everything is more controlled. Why? Because in this picture you are selecting a different set of response. Let's call them response. It is a dynamic convolution, acoustic convolution, but you are selecting a different set of response which are making your loud section less loud, and at the end you add a sort of make-up gain, and everything is more controlled. So you are trying to apply a different response to different section of your audio source, and you are controlling gain in that way, because at the beginning there is this detector, this envelope follower. When a loud input is in input, a quite impulse response is applied, so the overall gain is quieter. And at the end, all the sections have a better gain, because they are on the same level, more or less. In this case, in this example, that compressor was compressing about 7 dB, which is not very much. Anyway, you can make even an harder compression using a different ratio value. As you can see, we have a lot of contours here. We have a threshold, we have a ratio. We have a sort of control also for head. There is drive, we see it later, it's not important. And there is this makeup gain. So we can increase it again and have this result. Okay, let's go on. I told you we have a sort of clean convolution. Next step is how to add distortion again, because we started from something which was clean, alive but clean. But you miss harmonics. Okay. There is a convention paper from a researcher, an Italian researcher, Angelo Farina, from Parma. This convention paper explains that your response is just one of your the terms you are using in a more complex math formula. And you can model harmonics like they were a sort of convolution terms. This is a Bode diagram. On the left you have a clean version, because you have an input 1 kHz and you see there are no harmonics. On the right you have harmonics. How can we model it? There is a different math formula which is more complete, which is the Volterra series. There are a number of infinite terms in this formula. We are interested mostly in harmonics. And we are not interested in intermodulation, for example. So we can reduce the number of terms to few ones. The most important result is that each term could be described by a sort of impulse response. So, for example, first term is the convolution, static convolution we described before. There is a first harmonic, which is another sort of term for convolution, and so on. And this is a good approach because it fits completely in our vision. If you look to dynamic distortion slide, there are few harmonics. Each one is a sort of Acustica convolution, so a slow convolution in time. And you have few terms, each one for each harmonic. The result is pretty new because it's alive. It's a sort of a live process, but you have distortion because you have harmonics which are well represented and they are well sampled. Sampling process is pretty simple. There is just a different tone which is based on a sort of logarithmic sine sweep. It is a bit like a prism, so like a prism where light came across, so there is a sort of diffraction, and you have all colors. You have a white color in input, and you have more colors in output. Using this particular test tone, you can isolate all harmonics and get a sort of response for each one. Okay, let's see it. This is our input is very clean. Okay, this is a clean source.
Can you play it for a bit longer?
Yes, yes. Try to. Okay. It's very clean. Yeah. And you can hear there's a bit of distortion, but it's alive. It's very natural, like tubes. So we are on the good solution, maybe. We just need to complicate it a bit. Okay. We need to add the time variable. For example, when you have a flanger, when you have Leslie effect, you have something which is behaving in a sort of a cyclic way. So we had an idea. If we have a sort of snapshot of our system, which is like a photo, and we take a few snapshots of our system, we can make a sort of movies of them, a movie of them. And the most important thing is that we have a lot of photos which are like samples. Is like discrete sampling. So all theorems on classic sampling theory are working. For example, Nyquist, Shannon, and so on. We have not just one sample. We have a description of the system which is a single sample. And they are put a description after the other one, like a sort of a movie. So for example, you have a flanger in your input, you take your first photo, which is the impulse response, then another photo, which is again the impulse response, then another photo again. After a while, you have something similar to your first impulse response, so there is a sort of a cycle. A cycle. So you can start from the beginning again. You can add easily this kind of movement, but also this time variable to your system. Our system is becoming more and more complex as we are, because each slide is adding an element in this presentation. Really is making our model more complex. We are taking account. First, we started with the movement, then we added distortion, we added, in this case, time, we added the knob controls or external variable controls. Is a complete picture of your element. In this case, we are adding time. I have a dense track because you need something with a lot of frequencies for listening, for hearing, for example, a flanger or a phaser. Okay, and a flanger is a pretty obvious. It's a sort of a cycle. And I can move, I can change the rate. I can go fast because the samples can be tuned at a different sample rate. For example, you can sample a classic phaser. as you can hear, the effect is really natural. They are moving, they are interpolating, they are changing. There is distortion, there is a lot of things, but altogether they are starting working as a more complex model, and there is a sort of fluid effect. We are moving, changing our response quickly without adding distortion. But we can add distortion if we want. It's very important. In this case, a phaser is a distorted effect. In the flanger case, you have a clean effect. So you need to keep all things splitted, separated. Let's go on. When you need to change quickly your response, maybe the better approach is the direct convolution. I'll explain it later. Anyway, is a matter of length size of your samples, both in partitional convolution that in direct convolution. If you need to model, for example, a reverb, direct convolution is not enough, because you are consuming too much CPU power. In frequency, the convolution is just a multiplication. So the fast Fourier transform approach is a better solution. There are consequences on that. Anyway, at the moment we are interested in modeling, for example, a moving reverb. We can do it. We just need to use a fast Fourier approach instead of the direct one. So our model is getting more and more complex. Our reverb, there are different harmonics. You have a sort of slow convolution. Slow convolution because you can change your response slowly. There is a reason, a technical reason. But you can manage longer kernels, so long tails. So you can get, for example, a reverb working. So main feature is distortion, okay, but it's long. So for the first time, you can hear a true MT reverb with a proper distortion on it, which is a plate reverb, where distortion is really important, and you can get it just from sampling. This is our track.
I'm wandering around on the streets, sleeping on the bridges, wake up in the morning and nowhere to tend to, yay, struggling on the street to try to survive.
And this is the processed one.
I'm wandering around on the streets, sleeping on the bridges, wake up in the morning and nowhere to tend to, yay, struggling on the street to try to survive. I need someone to rescue me.
I'm just keeping the effect very obvious, but you can get something very subtle.
I'm wandering around on the streets, sleeping on the bridges, wake up in the morning and nowhere to tend to, yay, struggling on the street to try to stop.
What is important in this reverb, you can have a different control for harmonics. So, for example, here you can hear, because there is also the other reverb section, but you can hear distortion in this reverb. Okay. This is also a little demo from Mirko, in this case, which is showing his reverb. And if you can.
So, Giancarlo and I met each other like 8 years ago when he was first coding Nebula. I'm there since the first day and was a beta tester since day one. I don't know how to put it. like that. And now, 8 years later, we have Nebula, like you can see it here, and the Nebula 4 was that one in the silver line. And I have taken over Analog in the Box last year, which was help from Niklas from Germany, now from me, and we always worked together the last years. And yeah, Giancarlo can show for a second the website.
No, this one.
Do we have the website for a second?
Okay.
Giancarlo?
I'm wandering around on the streets, sleeping on the bridges, wake up in the morning and nowhere to tend to, yeah. Struggling on the street to try to survive. I need someone to rescue me. I'm cold.
Okay.
Innocent people, life on the street is so wide.
So what,
I say.
So what we have here are the where's the website? Do we have still the website open? So I can show it. Maybe it's a bit cleaner for them. So I don't know if you already understand what Giancarlo was tried to say already. This engine can sample nearly everything what you have in analog gear. So it can be EQs, it could be dynamics and reverbs, or the tube stuff and stuff with distortion in it. And yes, we are doing stuff in the EQ ways, or we do stuff dynamics, or we do also stuff reverbs. And what you hear is from this library Phonocamptica, which is sampled from a big Danish firm. I think everyone knows what I mean, or who I mean. Where's Reaper? And you will hear, I have 5 presets, the whole library is around 50 presets. And you hear a chord verb. And you could see you have, on every preset you have these sliders. You can you can mix your dry levels with your FX levels, so you don't need especially a send for it. Yeah, so you can use it as insert. And yes, so that was the church. Do we have still another one? Sorry. So you load it exactly from this screen. You load every library. So everyone who knows how sampler are working or like Contact, you will switch through all your presets and then.
In the morning and nowhere to tend to, yeah. Struggling on the street to try to survive. I need someone to rescue me.
Okay.
As you can see, as you can hear, also the reverb effect is dynamic, which is really new, I think, in the audio world, because you have a lot of engines which are creating a sort of reverb effect using analog modeling, or using, for example, a static response. For example, using a static response and adding a sort of analog modeling on the top, or other tricks, for example, distortion. But based on sampling, I think this is just the first time you hear this kind of effect. And this is like a reverb which is alive. Also in this case, for example,
I'm wandering around on the streets, sleeping on the bridges, wake up in the morning.
Is moving, and is moving without creating distortion in this case. So when we need distortion, we add distortion. When we don't need distortion, we don't add it. And we can get, for example, a sort of clean representation of our unit but which is moving, which is alive, like the original one, without getting artifacts, for example. Okay. Let's go on. I anticipated this issue before. We have a sort of a direct convolution when we need to go really fast, because we have a short kernel, and we can just select a different one while maybe it should still be played, is not finished, so you can switch even at high sample rates. But when you are using the fast Fourier transform, you are trying to minimize the CPU load. So you are working in blocks. You can change simply your response, your kernel, while it's playing. You should wait for next incoming block. So you are a bit forced to the block size. So each method has advantages and drawbacks. First one is very CPU intensive, because you see there is a number of operations, but it's faster. You can be more dynamic. You can preserve your transient in a better way, for example, if they are moving, if they are changing. Second one is pretty slow, but you can reach longer tails, so you can model reverbs. So we tried to mix both techniques. We said, okay, we could use a direct convolution for the beginning of our kernel, and the fast Fourier convolution for the second one, using a sort of crossfading among them. So first one, which is the most important, because you have in general the loud spike in it, can be really quickly, can switch really fast. The second one is slow, and when you mix, you have a long tail which is moving slowly, and the direct section of your kernel which is moving really quickly and can help you modeling, for example, a compressor. So this is a sort of hybrid approach. We are mixing techniques, and we have at the end a sort of final result. This is an audio sample, and this is our complete picture. We have a multiband equalizer with many controls. It is dynamic. It's featuring distortion. There are many bands in it. It's based on long kernels for detail, so we can model, for example, even the low gain in a good way, because you know, when kernels are too much short and too much small, you can model really all frequency in the same way. So for example, in this case, I enable this Reaper. Okay, that is also our okay. Okay. It's under testing. Anyway, let's see if we have it again. If it doesn't crash, it means it doesn't work. Okay. But what's important is we are merging all techniques here. A and we have a sort of complete one. Okay, this is a trial, perfect. Okay. It's working, it's crashing, okay. Okay. We are lucky. It was our last example. Really, we are still bug fixing it. Okay. Okay. Now we can add other techniques on our model. For example, when you are using a sampling approach, you are a bit linked to, for example, converters, or maybe your unit is in a bad shape. Sometimes the original unit is maybe featuring a roll-off in high frequencies. So if you need a perfect version of it, you can change your response. For example, with a sort of bug fixing of your kernel. In this case, you can use minimum phase filters. You are comparing your original kernel with a perfect one. You are applying the same amount of correction to all your samples, and in such case you have a sort of flat tone which is just perfect, like in this picture. This approach is very useful during sampling, because you can get something useful for mastering, where you need all frequencies there, and just you apply a little modification, and you just are adding a few dBs, or even less, a fraction of dB sometimes. Okay, for example, here we have something which seems perfect, but it was sampled. But as soon as you move something, you see that it was there is a sort of invisible correction everything. This fixing, this roll-off in high frequencies and in low frequencies, it is providing a sort of perfect model, but you have the original unit, which is a bit like bug fixed. Okay. Again, we can improve it further. For example, we are making a sort of interpolation when we are switching from our samples. We have a sort of preset approach. We have different methods for making this interpolation, and we just created a list of presets. The library developer, when is sampling the particular unit, choose the best approach for what is sampling in order to minimize, for example, aliasing or distortion. Again, okay, if I change, which is this sort of preset, I can modify the behavior in order to minimize or increase the effect, or get a better compression, or get a sort of compromise. So, as you can see, this model is getting more and more complex as we are speaking. Last piece. I told you about the envelope detector, a follower. Okay. We said we can model it using a sort of algorithmic approach. Okay, we can sample it too. For example, we can use a square tone we can process it in our vintage compressor, for example. We get a sort of shape for attack release time. We can sample it using the usual sampling technique used before. So we can have all samples of this envelope follower detector, which could be used for modeling the right attack or release shape envelope of our unit. And as you can see, we are adding, for example, this is a folder created by the automatic sampler, is adding a lot of files which are named with this strange extension, which are a bit like wave files. They can be opened in a wave editor, and they a sort of sample of your envelope follower or detector. So we have a complex model. At the end, we have a sort of complex model which is pretty good for everything, because it's taking account time, distortion. You can even reduce or simplify it, but you can take in account the correct envelope follower. You can take all samples from all different ratios, from different knob values. You can add variables from the side. You can take in account distortion, long kernels, and so on. Okay, how it's composed, this engine? There are two main pieces. There are two main sections. There is one which is the section which is executing convolution for each harmonic. It's what we call kernel engine, and as you can see, we have just a sort of convolver, because for each harmonic you are just making a convolution. This is the convolution operator, and you are summing the result. There is a power of the input for each harmonic, and it's very simple and it is very modular. And there is the second section, which is our little surprise, because it's very simple. It's based on a sort of tree structure. We have a lot of kernels which are modeling in a sort of data structure, complex data structure, which is similar to the one you can see in game engines, which is our main job. At the end, we create a sort of game engine, but for audio. And there are the same rules. Like before, I told you, we are making a sort of movie of different photos, but each sample is not an audio sample, but is a representation of your system. Here, I'm telling you, we have a sort of game engine, like a first-person shooter, Doom, Quake. The same rules, the same building blocks, because they have a sort of tree. For example, from a perspective, they should calculate where walls, what is hidden, and so on. So you should understand how to merge all data. And when you have a sort of frame per second in a game engine, now we have a program rate, which is a program per second. It was the timer I described at the beginning. So we are not inventing really anything new. We are applying different concepts coming from different areas. For example, game from one side. We are picking another concept, which is a movie of a system on the other side. We are adding distortion from us. And we are gluing everything in a single creation, which is really powerful, but you are not inventing anything, because someone else already did it. So when you have a game engine which is processing quickly a free structure, you can apply the same rules here. So it's really a novel approach. This tree structure is simple as a structure, but can be really big. We can have hundreds or thousands of samples for each emulation, depending on how many knobs you are sampling. For example, a flanger can be easily 10,000 samples, and so on. And the word picture, which is named Aqua, is the kernel engine from one side and the vectorial engine on the other side. Vectorial engine is creating in real time, like a game engine, a sort of a perspective of your word. So is creating in real time the correct responses, which are then taken in account, are processed by the kernel engine, which are just making convolutions. But as you can see, both sections of our picture are really important and equally important, because like a game engine, vectorial engine should be really fast, because we have a sort of frame rate. On the other side, the kernel engine should be really fast, because we are doing convolution, a lot of convolution, because we are doing a sort of convolution for each harmonic, and we are doing sometimes using partitioned convolution, so in blocks. Sometimes they are shorter. Sometimes we need direct convolution. Just to show how complex it could be, direct convolution was all coded in assembler language, because for each kind of processor, Intel, of different architectures, depending on if it is implementing particular SIMD instruction or not, if is cached in a particular way or not, you should build a sort of inner building block. In this case, is an example for what is a convolution, direct convolution in assembler in one case. You should take in account all different processors for this reason before it was crashing our demo, because you need a lot of debugging. It's something which is really difficult to create, and when it works, it's something which is doing a complex task quite impossible. We are creating a sort of plugin using actual computers which are still slow, and we have 100 of instances in our computers in real time, which is an amazing result. Now, I explain very slowly and using my bad language, English language, our main techniques. Okay. It's not all, because there is a sort of corner, detailed corner at the end. But which is really our value? Because, okay, I described our main concept. You can go home, you can maybe start coding this night and getting sometimes something like our plugin, maybe in a few months, years, I don't know. But our value really is not the product itself. What it was realized, what was created using it. Meanwhile, because today we are our company started in 2007, so 7 years ago, our third-party community created a lot of things using it, which is our main value. We are speaking about 100,000 of sampling hour of work, which is something incredible, because audio market is really unique, and before you can get all these things sampled, debugged, fixed, tested, you can go to a community and they say, okay, this is a good model, this one is not working. My Mali is better than, for example, your emulation, or your emulation is better than my current Mali emulation. You need a lot of time, because you need a community which should work, you should help you debugging, you should spend this time working on your product. Number of released libraries is an incredible number. We are speaking about 600 of libraries. I'm not speaking of sampled things, libraries. For example, a library is a tube library. So there is a sort of museum of a big archive of what is possible. And I asked the number of real units, and this was an answer from David. It's a credit, okay. It explains really, we are speaking about a number we can even count anymore. We don't know. My company was like a sort of startup. I was doing another job. It was very paid because I worked in finance. Okay. I was forced to stop because really this year we can just continue doing our activity just without coding each hour of the day and support our community, because they are moving, they are sampling, and they need a lot of resources, and we just now need a lot of time in order to sort all things, because the thing itself is out of our control, and we need to support our people. And I think we have this important community because time ago we had this manifest. It's very simple. It's what I think about world. Today you can buy everything, pretty everything. Nowadays, just if you have money, you go in a shop, you buy. But Acustica is my company, I have a different idea. I think the real value is the knowledge. As you can see, I started from a game engine, so we need a lot of knowledge in different areas, and you collect them in order to make something which others are not doing, because there is a sort of hole, there is a lacking sometimes of skills, or sometimes there is a lacking of interest, or maybe bigger companies are not interested in what you are doing. And the real value, the real richness today is the knowledge. For example, we have this tool which is very powerful. There are a lot of emulation, but you need a lot of knowledge, because you need to know when there is time for an MT reverb or another reverb. So it's important you have the right skills and you spend time for getting them. Now, quickly, because this is, we are moving to a skinned version of our products, because we are sampling the audio section. We are trying to sample also the visual side. We are starting from 3D models, but we are starting using also a sort of sampling of the scanners, 3D scanners. So you can take your vintage unit, you can scan it, and you can skin it. We are copying everything. This is a little scoop. It will be in the last section, which I think is very interesting if you are coders or if you are geek. Nebula is really fast. So fast, we created a sort of a new technology. Then I started another startup, because I had a lot of time. And I created a sort of new database which is a really fast database like NoSQL. Is a new trend in database, which is one of the fastest in the market. We are beta testing it. Competitors here are Aerospike, which is one of fastest in-memory database around. Redis, which is another in-memory database, very fast and very popular, for example, for porno websites. And MongoDB, they have a lot of money, and our solution is performing better. So this is a promising tech. Now, you could ask, why you are speaking about a database? Because the core engine is the same. It's incredible. We created a plugin, and the core engine is used for doing another thing. And I'll explain in our first section. When I was speaking about that fast tree, the game engine, you can create something which is missing. Sometimes you start because it's missing. You create something in order to make better than others. You get a powerful technology and you say, wow, I can use it for other tasks. So for example, I can get a database. This solution is useful also for getting a sort of cloud plugins. Because, for example, when you have a sort of consistent hashing, this is this ring in this slide, so you have more instance of your DSP code. When a node is down, other nodes can work, or can continue, or can share memory or structures. So when I created a NoSQL distributed database, I created the second generation for the plugin. As you can see, there are different tasks, different areas, and you can merge them. It's not important if you are creating a plugin, a database, a social network. It's not important. You just start working on something, you improve it, maybe you find something new, like we did, and then you say, okay, I can apply on something else. For example, before I was speaking about this cool movie concept. It's cool because you can model everything, not only audio. If you have a system, you have many photos of a system, and they are in sequence, and you have all theorem you know from Shannon, Nyquist, everything, they work. You just are applying not to a sample, but to a system description or a different concept. This is a cool concept. You can apply to everything. Maybe tomorrow you think, okay, this was a clever idea, but I can do it not for audio, or I can do it for video. I can do it, for example, for modeling winds or airplanes. They need a lot of calculation in order to forecast, for example, winds and other forces on wings. You can apply what I told you in a lot of different ways. Okay. And now it will be very short because my presentation is slow, is boring. I know my English makes everything really hard to understand. But I want just to explain how simple ideas really are not so simple when you are trying to build them, really. Because you can have also clever concept, but you put them together, and now, for example, we have a complex model, and we need to optimize it, and it's very difficult to optimize. So, for example, the kernel engine, how could you optimize? I told you about partition and convolution. We have a particular version of overlap and add technique. There are many convention papers which are speaking about overlap and save. In this case, overlap and add is better. So this is a little scoop. Why is better? Because you can cache your system in a better way. So you have a sort of accumulator at the end. I can describe it really in an easy way. You have your input, which is x, okay. Then you taking a partition, you are making a zero padding in order to make correctly your fast Fourier transform. Okay. Now you have your big X, which is your X in frequency domain. You make your partition and convolution. In this case, you have a sort of big accumulator, which is under the summer. And as you can see, you can save a calculation because you can have just one inverse fast Fourier transform. But not only. This accumulator, which is in common among different pieces of the engine, could be processed in parallel way. For example, we used the CUDA approach from NVIDIA, but you can use a SIMD instruction from processors. So you have plenty of methods for taking advantage of this particular parallel structure. So overlap and save is not the good move. You need to tune it to find a different solution. Okay. This is a slide which is very famous on the internet. I was speaking before about direct Fourier convolution. You can just have a picture of how many samples we are speaking about. Because here for 64 samples, it's better to get direct convolution than fast Fourier transform. You have several advantages. You can switch your impulse response really quickly, but also you are making less calculation. So there is a sort of discussion on the internet about which method is the best one, because everyone says fast Fourier transform is the only way. It's not true, because if you have something which is making less calculation, you are making many less rounding errors. So it's very important you don't take just a book and you say, okay, this book is telling me that I need to make fast Fourier transform because is in the log n ballpark. It depends, really. You should test it, and after you discover that your main developers, your community says, wow, your direct convolution is sounding a better way than fast Fourier. And so you ask, why is sounding a better way? And you can demonstrate it. Sometimes your community knows, is aware about things before you. So if you have a large community, sometimes they are giving hints, and it's very important because you should be really open-minded. You should just not open a book and say, okay, this book is telling me is wrong. You should verify why, and sometimes you discover is really right. And now the nightmare. Okay, I told you we have one of the fastest database around. We have a fast game engine. Maybe I create also first-person shooters in the future. I don't know how we can go so fast. Okay. There are particular data structures which are named red-black trees. I know we are speaking about audio here, but it's useful to know there are different things around. So there are particular data structures. They were invented around the 80s from an engineer from Boeing airplanes. Okay. They are self-balancing trees. Okay. They are pretty simple. It's like a game. There are red and black notes. Leaves are black. The root is black. and the path from a node to all leaves should count the same number of black nodes. Okay, it seems simple, but it's not. If you go on Wikipedia and you check how many things you should understand in order to keep this tree balanced, is not easy. Because rules are simple, but you should follow them. Okay. This particular tree data structure is very important because there is a sort of a worst case which is guaranteed in some way. Insertion, deletion, and also search in this particular tree. But it's not good really, even if it is very popular, because you can do range queries quickly. What is a range query? You have a sort of ordered list of data. You need to know which is the next element. Okay. Red-black is a clever structure. But if you need to go to the next element, you need to work for your tree, and you are wasting time. So, there is a solution on a convention paper, okay, which is a piece of the solution because something was missing. Okay. They said, in a clever way, well, we can store our data in leaves, like in B-tree. B-trees are used by Oracle database. I know a lot of Oracle stuff because I was working in finance. Okay. So they are clever structure, and they can be linked using double linked list. So they are sort of bidirectional pointers. Okay. Now, if all data is stored in leaf, we can have a sort of fast range search because we are only leaves and they are linked using pointers. At the same time, we can insert elements quickly in a fast way because we can take advantage from this particular red-black structure, this self-balancing tree. So, this is a convention.
We're out of time for questions. Can we give this another 10 minutes and then move on because it's now gone past 8?
This is the last slide.
Great. No problem.
I am exactly in time. There is a solution about this insertion on a convention paper. It's pretty easy. When a leaf is full, you can take the middle element and use it in your red-black, adding this element. They don't say why it's working. I tell you why it's working. Because it's adding a sort of right leaf. So each time you are splitting a node, you are just adding a right leaf. But nobody till now explained in a public way how to do deletion. I want to tell you these structures are really powerful. You can get something like 80 million queries for seconds for a single core on a notebook. We are speaking about a powerful structure. It's why our plugin is really fast. We are using it. Okay. And this is the solution. You can delete a node from the red-black when it is the right leaf of something which is empty. That convention paper wasn't telling you it was the right leaf which was added. So I just discovered it and I use it, and it's working. Okay. Quickly, we have a community. I created also a social network in my spare time. It's a bit like a Facebook, but you can see people which are moving around in real time. I get in touch with people around you. It was just an experiment. We are doing videos and other stuff. I'm using things developed for the plugin, okay? And it's important, credits, because Volterra, Matt is described in this convention paper from Angelo Farina, which is speaking about us. So it's important I'm speaking about him. Okay. And the other one is the convention paper, which is about 023, which is not complete. They are not presenting the deletion. Okay.
Very much, Giancarlo. Could we, as we open the floor, could we use the magic voice capturing stick here, if anyone has any questions, just for the benefit of the recording? Thank you very much. Any questions? Great.
Thank you for a wonderful talk, Giancarlo.
Yes, I'm sorry because my English, I hope you understand something from me. I'm trying to go slowly, but it's the best I can do.
We understood very well.
Okay,
Thank
okay,
you.
okay. Thank you.
I had two quick questions. Firstly, if you have this time variant, amplitude variant, impulse responses,
yes.
You're generating a lot of data.
Yes.
Yes. What's the typical size of a model? And in case you want to mix that to the second question, what's the worst case scenario for a signal or system
There
to
is
model?
not a worst case scenario, because our third party community is composed by crazy people. So if someone is trying to sample it using a brute force attack and is not making simplification, I want this, that, I want time, I want distortion, I want... It can get easily even 1 gigabyte data or even more. And someone created complex models which are around 1 gigabytes. And this is really a trouble for us, because each time a developer creates something like that, there is a lot of debugging from our side, and we should take in account all computers of the world. Sometimes you don't have enough memory, you don't have enough CPU power and so on. Anyway, most of our community is creating common models which are pretty small. Sometimes they are few kilobytes, sometimes megabytes, and sometimes they are, in the worst case, we should maybe 100 megabytes is the typical size of an emulation. But it can be gigabytes. There was a developer which I stopped. I told him, stop doing it. Because we can manage all this data. Because maybe my computer, yes, this is an i7, but maybe we have a customer with a slower computer, less RAM. Okay. Okay.
When you were speaking about capturing the distortion,
okay,
did you say that you didn't look for the intermodulation?
Yes.
So
Yes, because first of all, there isn't a clear method for capturing intermodulation using sampling.
Okay.
Second one, we are creating audio units. So our main focus is about modulation on harmonics, on clear harmonics. We have second, third, fourth harmonics, and we are not taking account distortion among them. Maybe for modeling properly a guitar cabinet or a really a unit which is featuring a complex distortion, you need everything. But you know, Volterra kernels are an infinite number of terms. So maybe this approach is not the best one. You should take everything for the best thing it can do. For example, this method is good for tubes, very good, or tapes. In music, because you don't need too much noise among your harmonics. You need something, and we are speaking about complex effect. They are really expensive. Distortion is just maybe 10% of the overall sound. So just you need to model it properly. You just need few harmonics. Sometimes you even don't need too many harmonics.
Sure.
Okay.
I was just trying to understand your model.
Yes. We can reach till 20 harmonics. Maybe I'll do another session in the future, because on convention papers they reach just 5 terms, and we reached 20 using several tricks. Okay, but I think for a first lecture about this complex subject, adding too many things would lead to too much confusion. Because if I start speaking about math, maybe, okay, you see some clever formula, you say, okay, this is a new form, okay, you are adding elements, okay, you are maybe reaching this high number of kernels in this way, okay, but what is a kernel, and so you need a sort of introduction on the subject before going really deeply. But we solved a lot of things, you can guess.
Just a question about the kernels.
Yes.
From looking at the slides, it would seem that all the harmonic, for the part of Volterra sort of style convolution, all of the kernels seem to be one-dimensional, and then you're taking the signal, the input signal, raising, yes, for example, where it's showing the kernels as one-dimensional.
Yes.
And with the input signal raised to the power, to the relevant power. Mm-hmm. Is that more the case of that's not full Volterra, but sort of a simplified?
Yes,
Volterra?
This is a simplified. Yes, this
okay,
is a diagonal. We can be a
three-dimensional third.
Okay, we can have it more accurate. This is a Volterra diagonal, so is a simplified system because we are not taking account all terms of this equation. Yes, it's correct. Yes.
Obviously, up to 20 would be.
This was the same question. In a different way, is a good question. Is a simplification. We are taking account only few terms because we are interested in modeling properly particular harmonics, not everything, and not till the last term. Just we need a few harmonics. But what we are doing different. Our harmonics are not static, but they are dynamic. So they are moving in time. So we are adding a lot of complexities. So we don't need to get more terms from Volterra, which could be more consuming on CPU. We can get this clever approach about sampling different photos, and we have time. So we have less terms. We can have this clever approach. We have dynamic, so we have less terms, and so on. Our approach is a sort of a composition of techniques. At the end, when you merge all of them, you have a proper technique which is really close to the original model. You should take into account we are modeling audio, so we are not speaking something we should be really accurate till last digit of your formula. What you need is its work is acting like the original unit and is pretty close. So much close, some user can guess this is just an emulation. There was a lot of A/B tests in Israel. There is also Waves company. We have a developer which is teaching in a school there, and they did a lot of A/B tests among units using our technique, using Waves, other UAD and so on, and they discovered our one was really close. In most of the cases they couldn't say which one was the original and which one was the emulation. So sometimes you don't need to get really all these complex formula with all terms, because you can simplify it.
Actually, as I'm no longer chairman now, I can abuse my position by asking you a couple of questions of my own. I'll declare an interest. I actually worked as a DSP engineer at Focusrite for 6 years. We did a covert project, which while I was an employee I probably couldn't tell you about, but I can now. And we were looking at a way of improving on liquid technology and providing essentially our own license-free version. One of the things, while I was looking into EQs and compressors, one of the things that we found about dynamics compressors is perhaps the most important part of the fingerprint is not what it does to the audio signal, but how you develop the side chain from an incoming signal. Now, that's something you can't manage very easily using standard sampling techniques. Is there anything that you've done in order to capture the side chain accurately?
Sidechain is a consequence because you are speaking about compressor sidechain.
Following the actual getting the envelope
at the moment we are not modeling multiband sidechain, if your question is this one, but we have an approach for it. We are working on it. At the moment we are just modeling a compressor, and we are adding a sort of side chain just because we have an assessment which is on a different audio path. So it is selecting your block of samples differently, but you are making assessment of something different. Yes. So is how sidechain is working. If you want to model properly sidechain, you should take into account also, for example, if they are using a filter, for example, because you should detect it. We are working on that. Yes.
Okay. The other question is, my current role really, I'm managing the intellectual property of a startup. You've got quite an ingenious algorithm for traversing red-black trees that you showed us. How do you stop other people just stealing it? Because it's quite hard to patent that kind of technology.
Okay, I am an open source guy. I created this database, and it will be open source. It will be open source. This is an important question anyway, because this evening is missing the other side of my company, which is the business. Okay. Now
you have to eat after all.
I am open source. Doing open source, I'm working on a lot of projects. My wife is getting crazy. Okay. And I just start this year to work on a single project. Okay, so I was around to divorce from her. Okay. Sometimes you need anyway to get also a business approach. What I call a business approach, because in this case, if the project was just about me, everything was for free. Okay, and just need something donation just in order to develop it in my spare time. But there are so many people involved in our community that I can do it. I can take. The only thing I can take is to work it seriously and try to get a business in order to support them properly. So if there are people, companies which are spending a lot of time on our platform, is a sort of respect.
So the value is in looking after other people's data?
Yes, because they are working. And it's very important, a little detail. This audio market is unique, is really small. So the audio open source approach doesn't work. I should be honest. There are few companies which are using, basing their company on something like a sort of open source, but it's not working because at the end there are few customers, few people interested. For example, when you create a cool technology, you need a lot of people around. Cassandra, there are hundreds of people which are committing it, which are writing code, which are debugging. So for a database, it is a good move. But for an audio project, you need to take money in some way in order to invest, in order to spend them on people which are helping you in making this project bigger.
Okay, thanks for that. Are there any more questions before I wrap up? Well, okay, a couple of things I want to say. The first one is thank you very much, Giancarlo. Very entertaining talk. The second thing is that there will probably be a lecture next month. We haven't confirmed it yet, but the very next event we're doing is Up Your Output, which is a two-day student event in this very building over the weekend of the 8th and 9th of March. Now, if you have a wall that a lot of students look at, whether you're a student or a tutor, we have a lot of publicity posters here, and please garner your walls with them if it will attract more people, because it's going to be a great event. Last year's was great. This will be even bigger and hence greater QED. So thank you very much.